Okay, today we're going to look at Chapter 7, Section 2, Spanning Trees. Remember from yesterday, we talked about what makes a tree, and we learned yesterday that your edges equals your vertices, your n minus 1. So that makes it a tree. So today we're going to look at when is a graph not a tree. So sometimes it's easy to tell, other times it's not. If it is hard to tell, then we can use the redundancy formula, which is this formula here. It's your R value. Your redundancy, R, equals your edges minus your vertices plus 1. So that's a quick and easy way to tell whether or not a network is going to be a tree or not. Sometimes it's easy to tell, and sometimes it's not. If the R value is 0, it's a tree. If the R value is anything else, then it's not a tree. R value just means redundancy. It means extra edges that you don't need. So let's do a couple examples. So number 1, you can probably tell by looking at it, there are no circuits, it's all connected, so it's a tree. But let's try to go through it using our formula. So first things first, we're going to figure out, is it a network? And I would say yes, because all the vertices are connected. So this is a network. The next thing I would look at is, what is the R value? So remember, the R value is found by doing your edges minus vertices plus 1. So let's count the edges. I've got 1 here, 2, 3, 4. So my R value is edges 4 minus vertices, which is 1, 2, 3, 4, 5, plus 1. So 4 minus 5 is a -1. -1 plus 1 is 0. So my R value is 0. Since my R value is 0, that means it is a tree. So it is a network, and it is a tree. Number 2, let's do the same thing. Notice all the vertices are connected, so it is a network. Now I'm going to do my formula. So my R value is found by doing edges, which is 1, 2, 3, 4, 5, 6, 7, 8, minus vertices, which is 1, 2, 3, 4, 5, 6, 7, 8, plus 1. So my R value, 8 minus 8 is 0. 0 plus 1 is 1. So R value is anything but 0. It means it is not a tree. So you're probably looking at those two and thinking like, all right, why do I need to know the R value? I can easily tell that everything is connected and there's no circuit, so therefore it's a tree. I can easily tell that everything is connected and there is a circuit, so it's not a tree. So the reason we need to know R value is because sometimes you have graphs that are really complicated and confusing, like number 3. So number 3 looks like there might be a circuit. Maybe there is. It's kind of hard to tell with these lines overlapping. Notice this is not a vertex right here. This is just where the dots over, or where the edges overlap. So on a more complicated graph like that, we're going to figure out an R value by figuring out whether or not it meets our R value and tree criteria. So let's first figure out. Notice how all the vertices are connected, so it is a network. Now to find the R value, I'm going to do edges minus vertices plus 1. So we'll count and I'll try to go slow. Edges first. So this is 1, 2, 3, 4. This is 5. This one is 6. This one is 7. So I have 7 edges. Minus vertices, I've got 1, 2, 3, 4, 5, 6, 7, 8. Edges minus vertices plus 1. So my R value is 7 minus 8, which is a -1, plus 1 is 0. The R value is 0, it means it is a tree. So maybe some of you can look at that and tell right away there are no circuits. It looks like the lines overlap and it looks like they might come back to itself. But as you can see, if you were to leave this vertex, there's no way you're coming back to it. There's only one way to get from one vertex to another vertex in the entire graph. For example, if you want to get from this vertex to, say, this vertex, the only way to do it is to go up and diagonal. You couldn't get to it by another means. So therefore it is a tree. So now that we have all that, let's now learn last section, how to count spanning trees. So in this section, all of these graphs are going to be, are not going to be trees. So what I'm asking you to figure out is we're trying to count how many different spanning trees are there? How many different subgraphs could there be? For example, in this first graph, obviously it's not a tree because you have a circuit right here. So to make it a spanning tree, to make it a subgraph, you would remove one of those edges. For example, you would not remove this edge up here. If you took out that edge up there, it's no longer a tree because this vertex is not connected to the rest of your graph. Same thing for these three edges over here. You would not remove those. You could, however, remove these edges in here. So you could take out this edge right here. If you take out that edge, it is still a tree because you can still get from this vertex to this vertex by going around your shape. You could also remove this edge down here. You could also remove this edge right here. So the way we count spanning trees is you first want to find the circuit. In this case, our circuit is in the middle. Our circuit has a length of 1, 2, 3, 4, 5. Since it has a length of 5, that means we have 5 spanning trees. Number 2, we're going to do the exact same thing and count the number of circuits we have and then what is the length of each of those circuits. So I have one circuit over here, I have one circuit right here, and I have one circuit on the end. Let's count the length of each of those circuits. Let's start with the shape here. It has a length of 1, 2, 3, 4, 5, 6. The next circuit has a length of 1, 2, 3, 4. The last circuit has a length of 1, 2, 3. So just like we learned in our probability unit, when you're trying to do, this is an AND problem, you're trying to do this circuit and this circuit and this circuit to make a graph. So when we do AND, we want to multiply those numbers together. So I'm going to multiply 6 times 4 times 3. 6 times 4 is 24. 24 times 3 gives me 72. So there are 72 spanning trees. So what that means is that there are 72 different ways you could draw this graph to make it a tree. So one subgraph, for example, would be that if you remove this top edge right here, remove this edge right here, and remove this edge right here. You remove all three of those edges, you have a tree, and that's one of your 72 options. You could also remove the top edge here, the same edge here, but now I'm going to remove this edge over here on the far left or on the far right side. Let's make it a little bit more complicated. Number 3 and 4, these are our last two we're going to look at. So number 3, notice, looks very similar to number 2 in that you have multiple circuits. So let's first count the length of each one. So this circuit has a length of 1, 2, 3, 4, 5. This circuit has a length of 1, 2, 3, 4, 5. So I'm going to multiply 5 times 5. But here's the problem. Notice when I counted those edges, I counted this edge twice. So this is what we're going to call a shared edge. So I'm going to draw an arrow to that edge. I'm going to label that. I'm just going to write the phrase shared edge above that. It is a shared edge. When you have a shared edge, you want to take away one because you have a one shared edge, so you remove one of those edges. And then you multiply using your order of operations like you did back in 6th grade. So 5 times 5 is 25. 25 minus 1 gives me 24. So there are 24 different ways to make a tree out of this graph. Number 4, last one. Let's count the number of circuits. I've got a circuit here, this diamond shape. I've got a circuit here, this little parallelogram. I've got a circuit here, this rectangle. So I've got 3 different circuits. Let's count the length of each one. This circuit has a length of 4. This circuit has a length of 4. This circuit has a length of 4. So it seems pretty straightforward, except for, remember, I've got a shared edge right here. So notice these two graphs share an edge, not this one. This one is separate. They are separated by an edge. Notice up here, they were separated by a vertex. You can share a vertex all you want. These don't share an edge. If you share an edge, you have to take away one. So because of that, I'm going to take away one right here. So I want to think of it like order of operations. I want to think of it like I'm going to multiply first this section and then multiply this section. So first, the way I showed it, I want to do something first is I want to do that by putting it in parentheses. So I'm going to do 4 times 4 minus 1. And then I'm going to multiply by this 4 there on the end. So 4 times 4 is 16. 16 minus 1 is 15. Remember, do order of operations first. Don't do 4 minus 1 first. If you're getting 12 there, you're doing the 4 minus 1 first. Don't do that. Order of operations, do 4 times 4 first. You get 16. Minus 1 gives you 15. Bring down your times, bring down your 4. 15 times 4 gives you 60 as your answer. So there are 60 different subgraphs you could make from that graph because you can remove those edges to make a spanning tree. I hope that was helpful. That's 7.2 spanning trees.